the amazing truth about the billions of galaxies, a number so vast that it defies all human comprehension. More galaxies in the observable universe than grains of sand on all of Earth's beaches. And yet, what we see is barely a microscopic fraction of what truly exists out there. Galaxies that devour each other in collisions lasting millions of years. Invisible structures so massive that they attract thousands of galaxies toward unknown regions of space. Black holes with the mass of billions of suns, governing the destiny of every galaxy. Light that has traveled for more than 13 billion years to reach us, showing us galaxies that might no longer exist. And there are countless other mysteries you may have never heard of. Because tonight, on Night Science, we are going to explore truths about the universe that will forever transform your perception of reality. If you are fascinated by the mysteries of the cosmos and want to keep discovering the deepest secrets of the universe, subscribe now and turn on notifications. Every video is a journey into the unknown, and this one has just begun. The observable universe contains approximately 2 trillion galaxies, 2 million cosmic islands, each containing between 100 million and 1 billion stars. To put this into perspective, if you started counting galaxies at a rate of 1 per second, it would take you more than 63,000 years to finish. And that is only what we can see, because light travels at 300,000 kilometers per second, but the universe is 13.8 billion years old. This means that we can only observe a sphere of space whose radius is the distance light has been able to travel since the Big Bang. Beyond that horizon, there are countless galaxies that we can never see, separated from us, not by distance, but by the very limit of time. But here is the most unsettling truth. The universe is not only vast, it is expanding. And not only is it expanding, but its expansion is accelerating. Every second that passes, thousands of galaxies cross the cosmological horizon and disappear from our sight forever, moving away faster than the speed of light. Not because they are moving through space at that velocity, but because the space itself between us and them is stretching at a rate that not even light can overcome. This accelerated expansion is driven by something scientists call dark energy, a mysterious force that constitutes approximately 68% of the universe's total content. We do not see it, we do not fully understand it, but we know it is there because we see its effects. It is tearing the universe apart, pulling galaxies out of our reach, condemning them to eternal isolation in the infinite darkness of space. And what makes this even more extraordinary is that we live at a privileged moment in cosmic history. At this very instant, we can see billions of galaxies scattered across the night sky. We can study their light, analyze their composition, and track their evolution through time. But in the distant future, when dark energy has completed its work, the civilizations that arise will see an almost completely empty sky. Only a handful of galaxies in their local group will remain visible, while everything else will have vanished beyond the horizon, invisible and unreachable forever. Imagine waking up in that distant future. You look up at the night sky and see only darkness. A few stars from your own galaxy shine faintly. Perhaps 1 or 2 companion galaxies appear as dim smudges in the void, but beyond that, nothing. A seemingly empty universe with no evidence that billions of other galaxies ever existed. No clues about the Big Bang. No way to know that the universe had a beginning or that it was ever different. The very evidence of the true nature of the cosmos would have disappeared. We, on the other hand, live in the golden age of cosmic observation. Our telescopes can capture light that has traveled from the most remote reaches of the observable universe. We can see galaxies as they were when the universe was barely a few 100 million years old. We can track the evolution of these structures over more than 13 billion years of cosmic history. We are witnesses to a spectacle that future generations will never be able to witness. But the most astonishing thing of all is that every galaxy we see tells a story. Stories of birth in the chaos of the early universe. Stories of violent collisions that merge entire galaxies into new structures. Stories of supermassive black holes that devour stars and gas, launching jets of energy across millions of light years. Stories of stars being born, living, and dying, enriching the cosmos with the elements necessary for planets and perhaps for life itself. And all of this is happening right now, at this very instant, in billions of places scattered throughout the universe. As you listen to these words, stars are exploding in supernovae in distant galaxies. Black holes are colliding, sending gravitational waves ripping through the fabric of space-time. New stars are being born in clouds of gas and dust, initiating cycles that will last billions of years. The universe is not static. It is a place that is dynamic, violent, beautiful, and terrifying all at once. A place where creation and destruction occur simultaneously on scales that defy all comprehension. And we, tiny inhabitants of a rocky planet, orbiting an average star in a common galaxy, have developed the ability to observe all of this, to understand it, and to marvel at it. Tonight, we are going to immerse ourselves in the deepest secrets of these cosmic islands. We are going to explore how they are born, how they live, and how they die. We are going to discover the invisible forces that hold them together and the structures that connect them across unimaginable distances. We are going to confront truths that will transform your perception of our place in the cosmos. Prepare for a journey through space and time, to the very limits of the observable and perhaps to the edges of the comprehensible. When you look up at the night sky on a dark night, far from city lights, you can see approximately 2,500 stars with the naked eye. Perhaps you can also make out the milky band of the Milky Way, stretching across the firmament. If you are lucky, you might glimpse the Andromeda Galaxy as a faint smudge in the constellation of Andromeda. That is all your eyes can capture without technological aid. But that vision is deceptive, because among those visible stars, in the apparent darkness of space, there are billions of galaxies that your eyes simply cannot detect. Galaxies so distant that their light has traveled for billions of years to get here. Galaxies so faint that the most powerful telescopes ever built are needed to reveal their existence. In 1990, the Hubble Space Telescope aimed at a small region of space in the constellation of Ursa Major, a region that appeared completely empty, with no bright stars, no nebulae, nothing of apparent interest. Astronomers decided to leave the telescope pointed at that seemingly empty patch of sky for 10 consecutive days, continuously accumulating light. The result was the Hubble Deep Field image. What appeared in that image stunned the scientific community. In that tiny portion of the sky, no larger than a grain of sand held at arm's length, the Hubble detected more than 3,000 galaxies, 3,000 cosmic islands in an area that appeared completely empty, and each of those galaxies contained hundreds of billions of stars. But the story does not end there. In 2003, the Hubble performed an even deeper observation of the same type, this time in the constellation of Fornax. The result was the Hubble Ultra Deep Field, an image that revealed approximately 10,000 galaxies in an equally minute region of space. Galaxies whose light had traveled for more than 13 billion years, showing us what the universe was like when it was barely 5% of its current age. And then, astronomers performed a simple but chilling calculation. If that density of galaxies is representative of the universe in general, and if you extrapolate that number to the entire celestial sphere, the result is astounding. Approximately 2 trillion galaxies in the observable universe, 2 million cosmic islands, most of them completely invisible, even to our most powerful telescopes. But even that number of 2 trillion could be a dramatic underestimate, because that calculation only includes galaxies that are bright enough to be detected by our current instruments. What about the fainter galaxies? What about the dwarf galaxies, small structures containing only a few million stars? What about the galaxies that are so distant that their light has not yet had time to reach us? And here we arrive at one of the most disturbing truths of the cosmos. We cannot see the complete universe. There is a fundamental limit to what we can observe, not imposed by technology, but by physics itself. That limit is the cosmological horizon, the maximum distance from which light has been able to travel to us since the Big Bang. Currently, that horizon is approximately 46 billion light-years away. Wait, you might think, how can it be 46 billion light-years if the universe is only 13.8 billion years old? The answer lies in the expansion of space. While the light from those distant galaxies traveled toward us, the space between them and us was expanding, effectively increasing the distance that the light had to cover. This means that there are galaxies, potentially an infinite number of them, beyond that horizon that we will never be able to see, not because they are hidden behind something, but because their light will simply never reach us. The universe is larger than the observable universe, and the difference could be immeasurably vast. But even within the observable universe, there are galaxies that are disappearing from our sight at this very moment. The accelerated expansion of the universe is pushing distant galaxies beyond the cosmological horizon at an alarming rate. Every year that passes, approximately 20,000 galaxies cross that limit and are lost to us forever. And it is not just that they become fainter, they literally disappear. The light they emit can never reach us because the space between us and them is expanding faster than the speed of light. We will never see them again. No matter how advanced our technology becomes, no matter how long we wait, those galaxies are lost to us eternally. This raises an unsettling philosophical question. If something exists, but is fundamentally impossible to observe, does it somehow count as part of our universe? For all practical purposes, those galaxies beyond the horizon might as well not exist at all. From our point of view, they are beyond any possible causal interaction with us. We can never visit them. We can never receive signals from them. We will never know if they developed life or what secrets they might contain. And then, there is the problem of dark matter. The galaxies we can see, bright and beautiful as they are, represent only a small fraction of the universe's total mass. Approximately 85% of all matter is what scientists call dark matter, a mysterious substance that does not emit light, does not absorb light, and does not interact with electromagnetic radiation in any way. We can only detect its presence through its gravitational effects. The galaxies we see are embedded in vast halos of this dark matter, invisible structures that extend far beyond the visible regions of the galaxies. In fact, without dark matter, galaxies as we know them could not exist. The gravity of normal matter alone is not enough to hold these structures together as they spin at dizzying velocities. The Milky Way, our own galaxy, rotates at approximately 220 kilometers per second in our solar vicinity. At that speed, without something providing additional gravity, the stars on the outer edges of the galaxy should be flung out into intergalactic space, but they are not. They are trapped by the gravity of a massive dark matter halo that surrounds the galaxy, invisible but undeniably present. So, when we talk about 2 trillion galaxies in the observable universe, we are talking only about the visible structures. The invisible cosmic ocean of dark matter that surrounds and connects them is much, much vaster. It is as if the galaxies were small lights floating in a dark and unfathomable sea, islands of light in an abyss of darkness that constitutes most of physical reality. And that leads us to a humbling but undeniable conclusion. Everything we can see, all the stars, all the galaxies, all the planets, all the gas and interstellar dust, all the electromagnetic radiation traveling through space, all of that represents less than 5% of the total content of the universe. The rest is dark matter, dark energy, things we do not fully understand, but which absolutely dominate the cosmos. We live in a universe where the invisible far outweighs the visible, where the unknown totally eclipses the known, where every answer we find generates 10 new questions. And yet, from our tiny planet, we have managed to map billions of these galaxies, track their movement, understand their evolution, and marvel at their immensity. The cosmic ocean is deeper than we ever imagined, and we have barely dipped our toes in its waters. Among the billions of galaxies that populate the observable universe, some show us secrets that defy our comprehension of time itself. Galaxies so ancient that their light began its journey when the cosmos was barely emerging from its infancy. And what they reveal about those first moments of creation is so strange, so different from what we see today, that it seems almost impossible to believe we are looking at the same universe. In 2022, the James Webb Space Telescope, the most powerful astronomical instrument ever built by humanity, detected something that perplexed scientists. A galaxy whose light had traveled for more than 13.4 billion years. A galaxy that existed when the universe was only 330 million years old, barely 2.4% of its current age. To put this into perspective, imagine compressing the entire history of the universe into a single year. On that scale, this ancient galaxy would have existed on January 9th. Dinosaurs would have walked the Earth only on December 27th. The entire history of human civilization would have occurred in the last 14 seconds before midnight on December 31st. But the truly unsettling thing is not just how old this galaxy is, it is that it should not exist at all, at least not according to our previous theories about galactic formation. Cosmological models predicted that the first galaxies would be small, chaotic, barely distinguishable from simple star clusters. But this galaxy, and several others detected by the Webb, are surprisingly large, massive, and structured for their age. Some of these primordial galaxies contain billions of stars. They have masses equivalent to tens of billions of suns and show levels of organization that, according to scientists, should have taken much longer to develop. It is like finding a completely constructed skyscraper on a plot of land where you expected to see barely the foundations. How is it possible that such massive galaxies formed so quickly? This question is forcing astrophysicists to reconsider fundamental models about the evolution of the universe. Perhaps dark matter played a more important role in the early stages than we thought. Perhaps the first stars were much more massive and formed galaxies more quickly than modern stars. Or perhaps there is something fundamentally wrong with our understanding of the early universe. When we look at these ancient galaxies, we are literally looking backward in time. The light we detect does not show what these galaxies are like now, but what they were like more than 13 billion years ago. In fact, it is very likely that many of these galaxies no longer exist in their original form. They might have merged with other galaxies, been torn apart by collisions, or evolved to become unrecognizable. And here is one of the strangest aspects of observational astronomy. We can never know what happened to these galaxies after the moment we are observing. The light that shows us their current state would take billions of years to reach us, and by the time it arrives, humanity might have long disappeared. We are seeing ghosts of the cosmic past, frozen snapshots in time, with no way of knowing the rest of the story. The first galaxies were radically different places than the galaxies we see in the local universe. For starters, they were much smaller on average. Most were only a fraction of the size of the Milky Way, but what they lacked in size, they made up for in frenetic activity. These primitive galaxies were forming stars at incredible rates, often hundreds or thousands of times faster than modern galaxies. The reason is simple. There was much more gas available. The early universe was filled with enormous clouds of hydrogen and helium, the primordial material created in the first few minutes after the Big Bang. This gas, uncontaminated by previous generations of stars, collapsed rapidly under its own gravity, igniting in massive bursts of star formation. And these first stars were monsters compared to the Sunday. Many had hundreds of times the solar mass. They burned bright blue with surface temperatures reaching 50,000 degrees Celsius or more, and they lived incredibly short lives, barely a few million years before exploding in cataclysmic supernovae that seeded space with the first heavy elements. Those heavy elements, carbon, oxygen, nitrogen, iron, all the elements necessary for rocky planets and for life as we know it, did not exist at the beginning of the universe. They were forged in the cores of these ancient stars and dispersed by their violent deaths. Every atom of carbon in your body, every molecule of oxygen you breathe, every atom of iron in your blood was created inside a star that died billions of years ago. The first galaxies were essentially heavy element factories. They processed primordial gas through generations of massive stars, gradually enriching the interstellar medium with the chemical diversity that would eventually allow the formation of planets, asteroids, comets, and life. Without these ancient galaxies and their frenetic star formation activity, the universe would still be a monotonous place, composed only of hydrogen and helium. But forming stars at that rate has consequences. Frequent supernovae released enormous amounts of energy into the surrounding medium, heating the gas and expelling it out of the galaxies. Powerful stellar winds from massive stars dragged material into intergalactic space, and when the black holes in the centers of these galaxies began to feed, they launched jets of radiation so intense that they could completely halt the formation of new stars. This process, known as feedback, is crucial for understanding why galaxies did not convert all their gas into stars. Without feedback, primitive galaxies would have consumed all their fuel in a few 100 million years, leaving the universe full of dead galaxies long before life had a chance to arise anywhere. Instead, feedback established a delicate balance. Galaxies formed stars. Stars exploded. The energy from the explosions expelled gas. The gas eventually cooled and fell back, and the cycle began again. This process of cosmic respiration allowed galaxies to sustain star formation for billions of years, creating the complex and diverse structures we observe today. The first galaxies were also extremely violent places. Galactic collisions were much more frequent in the early universe because galaxies were closer to each other. When two of these primitive galaxies collided, the result was spectacular. Massive bursts of star formation, shock waves tearing through the intergalactic gas, black holes merging and releasing unimaginable amounts of energy in the form of gravitational waves. And these collisions were not isolated events. A typical galaxy in the early universe might have experienced dozens of major mergers during its first billion years of existence. Each collision added more mass, more stars, more gas. Galaxies grew through this process of violent accretion, gradually merging into increasingly larger structures. That is why the large galaxies we see today, like the Milky Way, are actually amalgams of hundreds of smaller galaxies that merged over time. When astronomers analyze the orbits and chemical compositions of different stellar populations in our galaxy, they can reconstruct the history of these ancient mergers, identifying which stars originally belonged to dwarf galaxies that were devoured billions of years ago. But perhaps the most fascinating aspect of these primitive galaxies is what we cannot see. Among the first stars to form in the universe, there must have existed a population of even more massive and exotic stars, known as population 3 stars. These hypothetical stars, composed entirely of hydrogen and helium, without any heavy elements, might have had masses of hundreds or even thousands of times that of the Sunday. We have never directly observed a population 3 star, because by the time the universe was old enough for us to see the primitive galaxies with our telescopes, all these primordial stars had already lived and died, but they left indirect evidence of their existence. The patterns of heavy elements we see in the oldest stars that still exist suggest they were enriched by supernovae of extremely massive stars. And some scientists propose that the most massive population 3 stars might have collapsed directly into black holes without exploding into supernovae. These primordial black holes could be the seeds that eventually grew to become the supermassive black holes we see in the centers of current galaxies. It is a tempting hypothesis that connects the first stars of the universe with the most extreme objects we know. The early universe was, in short, a place of extremes, denser, hotter, more violent, and more active than anything we can observe in the local cosmos. The galaxies of that era were natural laboratories, where the limits of physics were tested, where conditions would never be repeated throughout the subsequent history of the universe. And every new discovery we make about these ancient galaxies rewrites our understanding of cosmic evolution. The James Webb Space Telescope has barely begun its observations, and it has already found galaxies that should not exist, structures that defy our models, enigmas that will keep astrophysicists busy for decades. The early universe still holds secrets that we are just beginning to unravel. When time was young, the rules of the cosmos were different, and the traces of that ancient era remain etched in the light that travels toward us from the most remote confines of the observable space. If you thought the universe was a peaceful place, where galaxies float serenely in the vacuum of space, prepare to discover a darker truth. Galaxies are cannibals. They devour each other in processes of unimaginable violence that unfold over millions of years. And our own Milky Way, the home of our solar system, is one of the most voracious galaxy devourers in our cosmic neighborhood. At this very moment, as you listen to these words, the Milky Way is actively tearing apart several dwarf galaxies. The Sagittarius dwarf spheroidal galaxy, a small collection of stars that was once an independent entity, is being ripped apart by the tidal forces of our galaxy. Its stars are being stripped away and absorbed, leaving only long filaments of stellar material that coil around the galactic disk like cosmic serpents. Astronomers have discovered evidence of at least 50 dwarf galaxies that the Milky Way has devoured throughout its history. 50 cosmic islands that once had their own identity, their own stellar populations, their own stories. Now their stars are scattered throughout our galaxy, mixed with the native stars, their identities erased, except for the subtle chemical and kinematic signatures that betray their foreign origins. And this is not a phenomenon unique to the Milky Way. Practically all large galaxies in the universe have grown through this process of galactic cannibalism. Galaxies are not born large. They start as small structures that gradually accumulate mass, merging with smaller neighbors, devouring anything that gets too close. It is a survival of the biggest process, where size dictates destiny. But when two galaxies of comparable size collide, the result is not a simple merger. It is a cataclysmic event that completely transforms both structures. Individual stars rarely collide. The space between them is too vast, but the enormous gas clouds within the galaxies do collide, violently compressing and igniting in massive bursts of star formation. The most famous galactic collision, visible from Earth, is the system known as the antennae galaxies, two spiral galaxies that are in the full process of merging, approximately 45 million light-years away. Images from the Hubble telescope reveal long arms of stars, gas, and dust that extend into space, ripped away by the gravitational forces during the encounter. In the regions where the gas clouds of both galaxies collide, thousands of young star clusters shine brightly, each containing tens of thousands of newborn stars. This collision began approximately 200 million years ago and will take another hundreds of millions of years to complete. In the end, the two spiral galaxies will merge into a single elliptical galaxy, a more rounded and less organized structure than the original spirals. All the stars from both galaxies will survive the process, but their orbits will have been chaotically transformed, erasing the elegant spiral structures forever. And the Milky Way will not escape this fate. Astronomers have calculated that in approximately 4.5 billion years, our galaxy will collide with the Andromeda galaxy, our closest spiral neighbor. Andromeda, which is currently 2.5 million light-years away, is approaching us at approximately 110 kilometers per second. The collision is inevitable. When the two galaxies finally meet, the night sky from Earth, if anyone is there to see it, will be spectacular. Andromeda, which currently appears as a faint smudge, barely visible to the naked eye, will dominate the sky as a huge and brilliant structure. As the galaxies interpenetrate, the sky will be filled with new stars, brilliant clusters of star formation, and the chaotic beauty of two stellar systems merging. But do not worry about the Earth. The odds of any star from Andromeda colliding directly with the Sun or any star from the Milky Way are astronomically low. The distances between stars are so vast that even during a head-on galactic collision, the stars will simply pass by each other like ghosts in the night. The solar system will likely survive the event relatively intact, although it might be ejected into a completely different orbit within the new merged galaxy. Scientists have already given a name to the resulting galaxy, Milkomeda or Milkdromeda, a combination of Milky Way and Andromeda. It will be a giant elliptical galaxy, much more massive than either of its progenitors, containing more than 1 trillion stars. And eventually, after billions of additional years, this supergalaxy will probably devour the other minor galaxies in our local group as well, growing even larger. But galactic collisions do not just redistribute stars, they also dramatically affect the supermassive black holes in the centers of the galaxies. When two galaxies merge, their central black holes eventually sink toward the center of the new merged galaxy. There they orbit one another in an increasingly tight gravitational dance, losing energy by emitting gravitational waves. This dance continues for millions of years, with the black holes gradually approaching. Finally, when they are separated by only a few Schwarzschild radii, the emission of gravitational waves becomes so intense that the black holes merge in a fraction of a second, releasing more energy than all the stars in the observable universe combined during that brief instant. In 2015, the LIGO detectors captured the gravitational waves from a black hole merger for the first time. It was a relatively small event, two stellar mass black holes merging more than 1 billion light-years away. But when the supermassive black holes in the centers of colliding galaxies finally merge, the resulting gravitational waves will shake the fabric of space-time across billions of light-years. These supermassive black hole merger events are some of the most energetic phenomena in the universe. In the final moments before the merger, the black holes orbit one another at a significant fraction of the speed of light. The space-time in their vicinity is distorted in extreme ways, creating complex patterns of gravitational waves that carry information about the masses and spins of the black holes. And when they finally merge, the resulting black hole often receives a recoil kick due to the asymmetric emission of gravitational waves. This kick can be powerful enough to eject the merged black hole completely out of the host galaxy, sending it wandering through intergalactic space at velocities of thousands of kilometers per second. Astronomers have found evidence of several of these runaway black holes ejected from their host galaxies by violent mergers. But not all galactic collisions are head-on. Many are grazing encounters where the galaxies brush past one another, distorting their structures but not merging completely. These close encounters can trigger bursts of star formation, create bridges of material between the galaxies, or rip off long tidal arms that extend into intergalactic space. A spectacular example is the system known as the Cartwheel Galaxy, a galaxy that was struck head-on by a smaller galaxy approximately 200 million years ago. The impact created a shock wave that propagated outward through the galactic disk, compressing the gas and triggering star formation in an expanding ring. The result is a galaxy that looks literally like a giant cartwheel in space, with a bright core and an outer ring of young blue stars. And then there are the galaxies in the centers of massive galaxy clusters. These giant galaxies, known as CD galaxies, are in the process of devouring almost everything in their vicinity. Sitting at the bottom of the cluster's gravitational well, they constantly attract smaller galaxies that stray too close. Over time, these CD galaxies can grow to contain trillions of stars, becoming the largest monsters in the universe. An impressive example is the galaxy IC 1101, located at the center of the Abell 2029 cluster. This galaxy has a diameter of approximately 6 million light-years, more than 60 times the diameter of the Milky Way, and contains approximately 100 trillion stars. It is so massive that its gravity completely dominates the entire cluster, orchestrating the movement of hundreds of other galaxies around it. These giant cannibal galaxies continue to grow in the present. Every few 100 million years, they devour another dwarf or intermediate-sized galaxy, adding its mass to their already vast reservoir of stars. In the distant future, if the universe were not expanding at an accelerating rate, eventually, all the galaxies in a cluster might merge into a single, monstrous supergalaxy. But the accelerated expansion of the universe is changing the rules of the game. As the space between galaxy clusters expands faster, mergers between galaxies from different clusters become increasingly unlikely. In the distant future, each galaxy cluster will be completely isolated, with no possibility of interacting with other clusters. Galactic mergers will continue within each cluster, but the universe as a whole will become increasingly fragmented. Still, within our own local group of galaxies, the process of galactic cannibalism will continue for billions of years more. The Milky Way will eventually absorb all the dwarf galaxies in our neighborhood. The merger with Andromeda will create Milkomeda. And finally, in an incredibly distant future, perhaps even the Triangulum Galaxy, the third largest member of our local group, will also be devoured. Galactic cannibalism is not an aberration. It is the norm. It is how galaxies grow, how they evolve, how they become the massive and complex structures we observe today. Every large galaxy has a violent past, a history written in the orbits and compositions of its stars, a memory of all the victims it devoured on its path to greatness. And in the grand cosmic scheme, even this process of violence and destruction has a purpose. Galactic mergers mix the material from multiple generations of stars, distributing heavy elements more widely, creating the conditions for new generations of star and planet formation. From the ashes of destroyed galaxies are born new stars, new planetary systems, new opportunities for life to arise in the cosmos. The universe does not build its largest structures gently. It forges them in violent collisions that last millions of years, in a process of simultaneous construction and destruction that has molded the cosmos since the beginning of time. At the heart of almost every galaxy in the universe, hidden behind veils of gas and dust, lurks a monster, a black hole so massive that it contains the mass of millions or even billions of suns, compressed into an infinitely small point. These cosmic titans, known as supermassive black holes, govern the destiny of their host galaxies, with an influence that extends across thousands of light years. The supermassive black hole at the center of our own Milky Way is called Sagittarius A star. It has a mass of approximately 4 million times that of the Sun, compressed into a region smaller than the orbit of Mercury. To put this into perspective, if you could travel towards Sagittarius A star at the speed of light, it would take you barely 20 seconds to cross its event horizon, the point of no return, beyond which not even light can escape. In 2022, the Event Horizon Telescope, a global network of radio telescopes working in conjunction, managed to capture the first direct image of Sagittarius A star. What appeared in that image was a bright ring of superheated gas orbiting around a central dark shadow. That shadow is the black hole itself, or more precisely, the region where gravity is so intense that light is captured before it can escape toward our telescopes. But Sagittarius A star is relatively small compared to the true monsters of the universe. At the center of the giant elliptical galaxy, Messier 8753 million light-years away, resides a black hole with an estimated mass of 6.5 billion suns. In the galaxy NGC 4889, there is a black hole that could contain up to 21 billion solar masses. And in the center of the Phoenix Galaxy cluster, astronomers have detected a black hole that could exceed 100 billion solar masses, 100 billion times the mass of the Sun, compressed into a region that, while technically larger than our solar system, due to how event horizons scale with mass, is still incomprehensibly dense. If you could somehow be near that black hole without being torn apart by tidal forces, you would see space-time distort in mind-bending ways. The light from distant stars would curve around the black hole, creating multiple ghost images of the same objects in different directions. But the question that obsesses astrophysicists is, how did these black holes get so large? Stellar mass black holes, those formed by the collapse of massive stars, typically have masses between 5 and 100 times that of the Sunday. Even if one of these black holes were at the center of a galaxy and could continuously feed on the surrounding gas, there is a physical limit to how fast it can grow. This limit is known as the Eddington limit. When a black hole feeds on surrounding matter, the friction in the accretion disk heats the gas to temperatures of millions of degrees. This superheated gas emits radiation so intense that it can push outward the material trying to fall into the black hole. There is an equilibrium where the outward radiation pressure equals the inward gravitational pull. This equilibrium sets a maximum rate of accretion. If a stellar mass black hole started feeding at the Eddington limit from the birth of the universe, it would take billions of years to grow to reach barely 1 million solar masses. However, astronomers have discovered billion solar mass black holes that existed when the universe was less than 1 billion years old. These black holes did not have enough time to grow from stellar mass seeds through normal accretion. This suggests that they must have started much larger than expected. Perhaps they formed directly from the collapse of enormous gas clouds in the early universe, creating black holes of thousands or tens of thousands of solar masses from the beginning. Or perhaps conditions in the early universe allowed super Eddington accretion rates, where matter fell into the black holes faster than standard theory predicts. The mystery of the early supermassive black holes remains unsolved, and these monsters are not just sitting passively in the centers of their galaxies. When they actively feed, they devour gas, dust, and occasionally entire stars that venture too close. The material, falling toward the black hole, forms a spinning accretion disk, a spiral structure where matter is heated to extreme temperatures due to friction. The inner regions of the disk can reach temperatures of 100 million degrees or more, shining brightly in X-rays. But not all the material approaching the black hole ends up falling into it. Something surprising happens in the innermost regions of the accretion disk. Powerful magnetic fields channel a fraction of the material outward, perpendicular to the disk, launching it into space in relativistic jets. These jets can extend over millions of light years, traveling at velocities that approach the speed of light. Astronomers have observed these jets emanating from the centers of galaxies throughout the universe. One of the most impressive is the jet from the galaxy Messier 87. This jet extends for approximately 5,000 light-years from the galaxy's nucleus, shining brightly in radio waves and X-rays. Calculations show that the total energy contained in this jet is equivalent to the rest mass energy of several million suns. It is as if the central black hole were converting matter directly into pure energy and launching it into space. These jets are not just spectacular, they have profound effects on their host galaxies. When a jet tears through the intergalactic gas, it creates enormous bubbles of hot gas that can extend for hundreds of thousands of light years. These bubbles heat the surrounding gas, preventing it from cooling and collapsing to form new stars. In effect, the supermassive black hole can completely shut down star formation in its galaxy. This process, known as active galactic nucleus (AGN) feedback, is crucial for understanding why the most massive galaxies have stopped forming stars. Without this feedback, giant galaxies would have converted all their gas into stars long ago, becoming much brighter than what we actually observe. Supermassive black holes act as regulators, controlling when and where new stars can form. But the influence of these black holes is not limited to regulating star formation. There is also evidence that a close correlation exists between the mass of the supermassive black hole in a galaxy's center and the mass of that galaxy's stellar bulge. This relationship, known as the M-sigma relation, suggests that black holes and their host galaxies evolve together, each influencing the growth of the other. How is it possible that a black hole, occupying such a tiny region compared to its host galaxy, can influence the evolution of the entire galaxy? The answer lies in the tremendous energetic power that black holes can deploy when actively feeding. Although the black hole itself is small, the effects of its feeding extend far beyond its event horizon, and there are times in a supermassive black hole's life when its activity reaches absolutely extreme levels. These periods, known as quasar phases, occur when the black hole is feeding at rates near or above the Eddington limit. During these phases, the galaxy's nucleus can shine with a luminosity equivalent to that of hundreds of trillions of suns, exceeding the combined brightness of all the stars in the galaxy. Quasars are the most luminous objects in the known universe. The brightest ones can be detected at distances of more than 13 billion light-years, showing us what they were like when the universe was less than 1 billion years old. A single quasar can illuminate its surroundings so intensely that we can see details of the intergalactic gas around it, gas that would otherwise be completely invisible. But these quasar phases are relatively brief in cosmic terms. They typically last between 10 and 100 million years before the black hole consumes all the easily accessible gas in its vicinity. Afterward, the black hole enters a quiescent phase, waiting for new galactic mergers or gravitational perturbations to push more gas toward the galaxy's center. Our own black hole, Sagittarius A star, is currently in one of these quiescent phases. It feeds on a very tenuous stream of gas, producing only a faint luminosity compared to what it could achieve. But this was not always the case. Astronomers have found evidence that only a few million years ago, Sagittarius A star underwent a much more intense phase of activity, launching giant bubbles of hot gas above and below the galactic plane. These structures, known as the Fermi bubbles, extend for approximately 25,000 light-years on each side of the galactic center. They were discovered in 2010 by the Fermi Gamma-ray Space Telescope. Their exact origin is still debated, but the most probable explanation is that they were created by a burst of activity from the central black hole, or by an extraordinarily intense burst of star formation in the galactic nucleus. And then there is the unsettling question: what happens if you get too close to a supermassive black hole? The answer depends on the size of the black hole. For a small stellar mass black hole, the tidal forces at the event horizon are so intense that they would tear your body apart into individual atoms long before you cross the point of no return. This process, known as spaghettification, would stretch your body into a thin filament due to the difference in gravitational pull between your head and your feet. But for a sufficiently large supermassive black hole, the tidal forces at the event horizon might be surprisingly gentle. You could cross the event horizon without feeling anything unusual at that moment. Only later, as you fall toward the central singularity, would the tidal forces eventually tear you apart. But you would have time, perhaps hours for the largest black holes, before that happened. Of course, this is purely theoretical. You could never report your experience to the outside world. Once you cross the event horizon, there is no way to send signals outward. From the perspective of an external observer, you would appear to slow down as you approach the horizon, your image becoming increasingly red and faint, effectively freezing in time right at the edge of the black hole. But from your perspective, you would cross the horizon and fall toward the singularity in a finite amount of time. Supermassive black holes represent one of the greatest enigmas of modern physics. They combine the most extreme predictions of general relativity with quantum effects that we do not yet fully understand. At the singularity in their center, where all the mass is compressed into an infinitely dense point, the equations of physics break down. The curvature of space-time becomes infinite, and current theories cannot tell us what truly happens there. Solving this enigma will probably require a theory of quantum gravity, a unified description that combines general relativity with quantum mechanics. Physicists have been working on this for decades, but a complete theory still eludes us. Perhaps, when we finally solve the mystery of what happens in the heart of a black hole, we will discover even stranger truths about the fundamental nature of reality. Meanwhile, these cosmic monsters continue to govern their galaxies, shaping the evolution of the universe in ways we are just beginning to comprehend. They are the most extreme creatures predicted by the laws of physics, and yet they are everywhere, lurking in the centers of practically every galaxy in the observable cosmos. Hidden behind the plane of our own Milky Way, invisible to our optical telescopes due to the dense clouds of dust and gas that block the view, exists something that is attracting our galaxy, along with thousands of others, toward a specific region of space. Astronomers call it the Great Attractor, and we cannot see it directly, but we know it is there. We know because of the way the galaxies move. The Milky Way is not simply floating adrift through space. It is being dragged, along with our entire local supercluster of galaxies, toward a region located approximately 250 million light-years away in the direction of the constellations of Hydra and Centaurus. The velocity of this movement is approximately 600 kilometers per second, in addition to the movement caused by the expansion of the universe. 600 kilometers per second, that is more than 2 million kilometers per hour. Our entire galaxy, with its 200 billion stars, is falling towards something so massive that its gravity dominates the dynamics of tens of thousands of galaxies across hundreds of millions of light-years. And for decades, astronomers had no idea what that something was. The Great Attractor was discovered in the 1970s, when astronomers began to map the peculiar velocities of galaxies. Peculiar velocities are the movements of galaxies, in addition to the movement caused by the expansion of the universe. By measuring these velocities for hundreds of galaxies, scientists discovered an unsettling pattern. Almost all the galaxies in our cosmic neighborhood were moving in the same general direction. But directly observing the region of the Great Attractor is almost impossible. It is located behind the zone of avoidance, a region of the sky blocked by the dense disk of our own galaxy. It is like trying to see through a thick forest. The dust and stars of the Milky Way absorb and scatter the light from anything behind it, effectively leaving us blind to what is there. However, using X-ray and infrared telescopes that can partially penetrate the galactic dust, astronomers eventually discovered that the Great Attractor is not a single object. It is a complex of multiple massive galaxy clusters concentrated in a region of space. The main component is the Norma cluster, a collection of galaxies so massive that its gravity affects the movement of structures hundreds of millions of light-years away. But the story gets even stranger. In the 2000s, astronomers discovered that the Great Attractor itself is being pulled by something even larger, a truly colossal structure known as the Laniakea supercluster, of which our local supercluster is barely a peripheral part. Laniakea is one of the greatest discoveries of modern astronomy. It is a structure spanning 500 million light-years in diameter and containing approximately 100,000 galaxies with a total mass of 100 trillion suns. The name Laniakea comes from the Hawaiian and means immeasurable heavenly horizon, an appropriate name for a structure so vast that it defies human comprehension. And Laniakea is not the largest structure we know. Superclusters, like Laniakea, are connected to each other by filaments of galaxies that form what astronomers call the large-scale structure of the universe, also known as the cosmic web. If you could zoom out far enough from the universe to see this structure in its entirety, you would see something that looks surprisingly like a spiderweb or the neural connections in a brain. There are long, thin filaments of galaxies that stretch across hundreds of millions of light-years. These filaments are connected at nodes where multiple filaments meet, creating massive superclusters, and between the filaments are voids, regions almost completely devoid of galaxies that extend for tens or hundreds of millions of light-years. These voids are unsettlingly empty. The Boötes void, for example, also known as the Great Void, is approximately 300 million light-years in diameter and contains only a few dozen galaxies. To put this into perspective, a typical region of the universe of that size would contain approximately 2,000 galaxies. It is as if someone had dug an enormous bubble in the fabric of the cosmos, leaving an almost perfect vacuum. Why is the universe organized this way? The answer goes back to the conditions of the early universe. In the first moments after the Big Bang, there were small quantum fluctuations in the density of matter. These fluctuations, amplified by cosmic inflation, became the seeds of all the structure we see today. The slightly denser regions attracted more matter through their gravity. This additional matter increased their gravity, attracting even more matter. Over time, the dense regions became denser, while the less dense regions emptied as their matter was drawn toward the denser regions. The result is the cosmic web of filaments and voids that we observe. But there is something particularly special about this structure: dark matter. The filaments of the cosmic web are not primarily made of normal matter like stars and gas. They are primarily made of dark matter, that mysterious substance that constitutes 85% of all the matter in the universe. The galaxies we can see are like decorative lights hung on an invisible Christmas tree. The tree, the structure that holds everything, is the dark matter. Astronomers have been able to map this invisible dark matter structure using a technique called weak gravitational lensing. The gravity of dark matter curves the light from distant galaxies in subtle ways. By analyzing these distortions in the apparent shapes of millions of galaxies, scientists can reconstruct the three-dimensional distribution of dark matter across billions of light years. And what they have found is astounding. The cosmic web of dark matter extends throughout the observable universe. It is like an invisible skeleton that supports the entire visible structure of the cosmos. Without this dark matter skeleton, galaxies could not have formed in the first place. The universe would be a much more uniform and boring place, probably incapable of sustaining the complexity necessary for life. But let us return to the Great Attractor and its role in this cosmic web. The Great Attractor is located approximately at the center of the Laniakea supercluster, acting as a gravitational node that organizes the movement of all the galaxies within the supercluster. All the galaxies in Laniakea are, in a very real sense, falling toward the center of the supercluster. However, here is the paradox. We will never get there. The accelerated expansion of the universe is pulling apart the large-scale structures faster than gravity can bring them together. Although we are falling toward the Great Attractor at 600 kilometers per second, the space between us and it is expanding even faster. It is like running on a treadmill that moves faster than you can run. No matter how hard you try, you will never move forward. In the distant future, the accelerated expansion will have separated all the superclusters until each one is completely isolated from the others. Laniakea will eventually fragment into its constituent local groups, and those local groups will be the only gravitationally bound systems left. Everything else will have been swept beyond the cosmological horizon by the relentless expansion of space. And there are structures even larger than superclusters. In 2013, astronomers discovered the Hercules Corona Borealis Great Wall, a structure that extends for approximately 10 billion light-years, containing billions of galaxies. It is the largest known structure in the observable universe, so vast that it defies the predictions of standard cosmology about how large cosmic structures can be. In fact, the discovery of such large structures has been problematic for cosmologists. According to the cosmological principle, a fundamental assumption in cosmology, the universe should be approximately homogeneous and isotropic on sufficiently large scales. In other words, if you zoom out far enough, the universe should look more or less the same in all directions. But structures like the Hercules Corona Borealis Great Wall challenge this notion. They are so large that they seem to violate the theoretical limit of how large structures can grow, given the age of the universe and the known laws of physics. Perhaps there is something about the formation of large-scale structures that we do not yet fully understand. Or perhaps these structures are extremely rare statistical fluctuations, cosmic anomalies that only appear to violate theoretical expectations. What is certain is that the universe on a large scale is much more structured and organized than anyone expected when the first galaxy surveys began. It is not a random distribution of galaxies scattered uniformly throughout space. It is a complex network of filaments, nodes, superclusters, and voids, organized in patterns that repeat on ever larger scales. And we, inhabitants of a modest galaxy on the periphery of Laniakea, are just beginning to map this structure in its entirety. Every new galaxy survey reveals more details of the cosmic web, more filaments, more voids, more complexities that challenge our understanding. The universe is like a giant, three-dimensional puzzle, and we have barely begun to assemble the pieces. But perhaps the most unsettling thing is this. Everything we have mapped, all these superclusters, filaments, and voids, exists only in the observable universe. Beyond the cosmological horizon, there are presumably similar structures, extending indefinitely, structures that we can never see, superclusters that we will never know. filaments of the cosmic web that extend beyond any possible observation. The Great Attractor reminds us that we are part of something much larger than ourselves, not just part of a galaxy, but of a group of galaxies, part of a supercluster, part of a cosmic structure that extends for hundreds of millions of light years. And all of this is being orchestrated by invisible forces, by the gravity of dark matter, by the push of dark energy, by dynamics that we are just beginning to comprehend. We are being dragged through space by gravitational currents that escape our direct perception. And even though we may never reach our destination, the journey itself reveals profound truths about the nature of the cosmos in which we exist. Not all galaxies are alive. Scattered throughout the universe exist galaxies that stopped forming stars billions of years ago. Dead galaxies, frozen in time, populated only by ancient stars that are slowly consuming themselves toward darkness. Astronomers call them red and dead galaxies, or more poetically, zombie galaxies. They are the cemeteries of the cosmos. The first time you look at one of these dead galaxies, you might not notice anything unusual. It still shines. It still contains billions of stars. But if you analyze its light carefully, you discover something unsettling. There are no young blue stars. There are no bright regions of star formation. There are no glowing nebulae where new stars are being born. Only a uniform reddish glow from old, dying stars. These galaxies are dominated by red dwarf stars and red giant stars. Stars that have exhausted the hydrogen in their cores and are in the final stages of their lives. They are galaxies in slow motion toward extinction. Over the next trillions of years, their stars, one by one, will go out. The remaining massive stars will explode in supernovae. The intermediate mass stars will expel their outer layers as planetary nebulae, and the small stars will simply cool down to become white dwarfs, stellar corpses that can no longer generate energy through nuclear fusion. But how does a galaxy die? What can stop star formation in a structure that contains billions of solar masses of available gas? The answer, like many things in astronomy, involves multiple processes working together to gradually kill the galaxy. The first galaxy killer is the galactic merger. When two galaxies collide, the shock waves compress the gas and trigger massive bursts of star formation. This sounds like something that would keep a galaxy alive. But the problem is that these bursts of star formation are so intense that they consume all the available gas in barely a few 100 million years. It is like burning all the fuel reserves at once. Afterward, there is nothing left for future generations of stars. The second killer is the supermassive black hole in the galaxy's center. As we saw in the previous chapter, when these monsters actively feed, they can launch enormous amounts of energy that heat the surrounding gas to temperatures so high that it cannot collapse to form stars. This process, active galactic nucleus, AGN, feedback, can effectively sterilize an entire galaxy. The third killer is the intergalactic medium. When a galaxy falls into a massive galaxy cluster, it finds itself surrounded by hot intergalactic gas. As the galaxy moves through this gas at velocities of thousands of kilometers per second, the gas inside the galaxy is literally stripped away by ram pressure, a process known as ram pressure stripping. It is like driving a convertible car at high speed. The wind rips away everything that is not firmly secured. Giant elliptical galaxies are the best examples of dead galaxies. These structures, which typically form from mergers of multiple spiral galaxies, contain trillions of stars but have almost no active star formation. Their light is dominated by old, red stars, giving them a characteristic reddish hue. They are the final monuments of galactic evolution, structures that have completed their life cycle and are now simply passively aging. But some dead galaxies show signs of resurrection. In rare cases, a dead galaxy can capture a gas-rich dwarf galaxy, or gas can fall from the intergalactic medium. This new fuel supply can restart star formation, creating populations of young stars in a galaxy that had been dead for billions of years. They are true zombie galaxies, dead but reanimated. However, these resurrections are typically temporary. Once the new gas is consumed, the galaxy returns to its dead state. The second death is generally permanent because sources of new gas become increasingly scarce as the universe ages, and more gas is locked into stars or expelled into the intergalactic medium. Now contrast these dead galaxies with the most active and violent objects in the universe, quasars. If dead galaxies are cosmic cemeteries, quasars are nuclear supernovae, explosions of energy so intense that they can be seen from the most remote confines of the observable universe. A typical quasar shines with a luminosity equivalent to that of 100 trillion suns, 100 trillion. To put this into perspective, our entire Milky Way, with its 200 billion stars, has a luminosity of approximately 25 billion suns. A single quasar can exceed the brightness of 500 galaxies, like ours combined. And all this energy comes from a region no larger than our solar system. Quasars are supermassive black holes in extreme feeding mode. When enormous amounts of gas fall toward the black hole, the accretion disk heats up to temperatures of millions of degrees, shining brightly across the entire electromagnetic spectrum, from radio waves to gamma rays. Friction in the disk converts approximately 10% of the mass energy of the infalling matter into pure radiation, a much more efficient energy conversion process than nuclear fusion in stars. The first quasar was discovered in 1963. Astronomers had detected a bright radio source that seemed to coincide with what appeared to be a faint star. But when they analyzed its spectrum, they discovered something completely unexpected. Spectral lines shifted toward the red by enormous amounts. This redshift indicated that the object was billions of light years away, which meant it had to be incredibly luminous to be visible at all. It soon became clear that these objects were not stars at all. They were the brilliant nuclei of distant galaxies powered by supermassive black holes. The name quasar comes from quasi-stellar radio source, reflecting their initial appearance as stars in optical images, despite their true nature as incredibly distant and luminous extragalactic objects. The most distant quasars we know existed when the universe was less than 1 billion years old. These ancient quasars are particularly puzzling because their central black holes already had billions of solar masses at that early time. As we discussed earlier, it is unclear how these black holes were able to grow so quickly in such a short time. One of the most distant known quasars is J03-1806, discovered in 2017. Its light has traveled for more than 13 billion years to reach us, showing us what this object was like when the universe was only 670 million years old. And yet, the black hole at its center already had a mass of approximately 800 million suns. The existence of such massive quasars so early in the universe's history suggests that the first black holes must have formed much faster than standard theories predict. Perhaps they formed directly from the collapse of enormous gas clouds, or perhaps they grew through super-Eddington accretion rates that violated normal theoretical limits. The mystery of the early quasars remains one of the great, unsolved enigmas of modern astrophysics. Quasars also profoundly affect their surroundings. The intense radiation from a quasar can ionize gas across millions of light years, creating giant bubbles of ionized gas known as proximity regions. These effects are so extensive that quasars can be used to study the intergalactic medium at great distances, illuminating gas that would otherwise be completely invisible. And quasars have a particularly useful characteristic for astronomers. They are so bright that they can be seen across almost the entire observable universe. This makes them cosmic lighthouses that can be used to study the large-scale structure of the universe. By analyzing how the light from distant quasars is absorbed by intergalactic gas on its way to us, astronomers can map the distribution of matter across billions of light years. But quasar phases are ephemeral in cosmic terms. They typically last between 10 and 100 million years before the black hole consumes all the easily accessible gas. Afterward, the quasar shuts down, leaving behind an inactive supermassive black hole at the center of a galaxy that may show the scars of its violent past. In fact, Many dead galaxies we see today probably went through quasar phases at some point in their past. The intense feedback from the quasar would have heated and expelled much of the galaxy's gas, halting star formation and condemning the galaxy to a slow death. In this sense, quasars are both creators and destroyers, forging the structures we see, but also planting the seeds of their eventual decline. And then there are the intermediate objects between dead galaxies and quasars, the Seyfert galaxies and the blazars. Seyfert galaxies have active nuclei, similar to quasars but less luminous, typically shining with the power of 1 billion to 10 billion suns instead of 100 trillion. They represent a phase of moderate activity of the central black hole, not as extreme as a quasar, but still much more active than a normal galaxy. Blazars, on the other hand, are quasars whose relativistic jets are pointed directly toward the Earth, due to special relativity effects. When we observe a jet moving almost at the speed of light directly toward us, its apparent brightness is enormously amplified. Blazars are some of the most variable objects in the sky, changing their brightness on timescales of hours or days, as perturbations in the jet pass through our line of sight. The diversity of active nuclear phenomena, from faint Seyfert galaxies to blazing quasars and violently variable blazars, reflects the complexity of the physics of supermassive black holes. Each type of object teaches us something different about how these cosmic monsters interact with their surroundings, how they grow, and how they eventually shut down. But perhaps the most striking contrast in the universe is between a completely dead zombie galaxy and a quasar in full fury. In the dead galaxy, time seems to have stopped. Stars orbit silently, slowly, aging, with no new births to renew the population. It is a place of stillness and inevitable decline. In the quasar, time accelerates to relativistic limits. Matter falls toward the event horizon at a significant fraction of the speed of light. Jets launch plasma into space at velocities that defy imagination. The energy released in seconds exceeds the sun's energy production over its entire lifetime. It is a place of extreme violence and creativity, where physics is tested to its limits, and both exist simultaneously in 180 different regions of the same universe. Dead galaxies floating silently in the vacuum, passive witnesses to their own decay. Quasars roaring through spacetime, lighthouses of energy that can be seen from the confines of the cosmos. Cosmic life and death, juxtaposed on the vast stage of the observable universe. The cosmos does not have a single destiny. It has many. And each galaxy will follow its own unique path into the future, determined by its mass, its history, its environment, and a touch of cosmic chance. Approximately 85% of all the matter in the universe is completely invisible. It does not emit light, it does not absorb light, and it does not interact with electromagnetic waves in any way that we can directly detect. We only know it exists because of its gravitational pull. Scientists call it dark matter, and without it, galaxies as we know them could not exist. Imagine you are trying to understand how a mechanical clock works, but 85% of its gears are invisible. You can see the hands move, you can hear the ticking, but you cannot see most of the machinery that makes everything work. That is essentially the situation astronomers face when trying to understand the universe. Most of what drives cosmic dynamics is hidden from our sight. The first clue to the existence of dark matter came in 1933, when the Swiss astronomer Fritz Zwicky studied the Coma galaxy cluster. By measuring the velocities of the galaxies in the cluster, he discovered something disturbing. They were moving too fast. Based on the amount of visible matter in the form of stars and gas, the galaxies should have been flung out of the cluster long ago, but clearly, they had not been. Zwicky calculated that there must be approximately 400 times more mass in the cluster than could be seen. He proposed that this invisible mass, which he called dark matter, provided the additional gravity needed to hold the cluster together. His initial calculations turned out to be exaggerated, but the fundamental idea was correct. There was something invisible exerting gravity. For decades, this idea was largely ignored. It seemed easier to assume there was some error in the observations or the calculations. But in the 1970s, the astronomer Vera Rubin conducted an exhaustive study of the rotation velocities of spiral galaxies. What she discovered confirmed Zwicky's suspicions and transformed our understanding of the universe. Rubin measured how fast stars rotated at different distances from the center of various spiral galaxies. According to Newton's laws, stars farther from the center should move slower, in the same way that the outer planets of our solar system move slower than the inner ones. But that is not what Rubin observed. The stars on the outer edges of the galaxies were moving as fast as the stars closer to the center. The only explanation was that the galaxies must be surrounded by massive halos of invisible matter that extended far beyond the visible regions. This dark matter provided the additional gravity needed to keep the outer stars moving at high velocities without being flung into intergalactic space. Since then, multiple independent lines of evidence have confirmed the existence of dark matter. One of the most convincing comes from the study of galaxy cluster collisions. The most famous example is the Bullet Cluster, two galaxy clusters that collided approximately 150 million years ago. When astronomers observed the Bullet Cluster using X-ray telescopes, they saw something fascinating. The hot intergalactic gas from both clusters, which constitutes most of the normal matter in the clusters, collided and slowed down due to friction, forming a bullet-shaped structure. But when they mapped the distribution of mass using gravitational lensing, they discovered that most of the mass had passed directly through the collision without slowing down. This is exactly what you would expect if most of the mass was dark matter that interacts only gravitationally. The dark matter particles from one cluster passed directly through the dark matter particles from the other cluster like ghosts, without colliding or slowing down. The Bullet Cluster provides direct visual evidence that dark matter exists and that it behaves fundamentally differently from normal matter. But what exactly is dark matter? This is one of the most important and frustrating questions in modern physics. We know a lot about what it is not. It is not made of normal atoms, because if it were, we would have detected its interaction with light. It cannot be ordinary black holes or dead stars, because there are not enough of those objects to explain all the missing mass. The most popular explanation is that dark matter consists of exotic subatomic particles that we have yet to discover. Physicists have proposed several candidates: WIMPs, weakly interacting massive particles; hypothetical extremely light particles called axions; and sterile neutrinos, heavier versions of the known neutrino particles. But despite decades of searching, using increasingly sensitive detectors, we still have not directly detected any dark matter particle, and the problem becomes even stranger when you consider the distribution of dark matter. It is not scattered uniformly throughout space. It forms structures, halos that surround individual galaxies and filaments that connect galaxies across millions of light years. These dark matter structures formed the scaffolding upon which all the visible structure of the universe was built. In the early universe, barely a few 100,000 years after the Big Bang, dark matter began to collapse under its own gravity, forming dense clumps. These dark matter clumps attracted normal matter, hydrogen and helium, into their gravitational wells. The normal matter accumulated in the centers of these dark matter halos, eventually collapsing to form the first stars and galaxies. Without dark matter, this process would have been much slower, or perhaps impossible. Normal matter alone could not have formed structures fast enough given the age of the universe. Dark matter acted as a catalyst, accelerating the formation of structure and allowing galaxies to form much earlier than would have been otherwise possible. The dark matter halos surrounding galaxies like the Milky Way extend far beyond the visible stars. Our dark matter halo probably has a diameter of approximately 600,000 light-years, more than 6 times the diameter of the galaxy's visible disk, and contains approximately 1 trillion solar masses, about 10 times more mass than all the stars, gas, and dust of the galaxy combined. This means that when you look at the Milky Way, you are only seeing a small fraction of what is truly there. It is like seeing the tip of an iceberg. The visible part is real, but there is a hidden mass under the surface that truly determines how the complete system behaves. And there is evidence that dark matter halos have substructure. They are not smooth, uniform spheres. They contain clumps, streams, and substructures created by dwarf galaxies that were torn apart by tidal forces and absorbed by the main galaxy. These dark matter remnants of devoured galaxies should be flowing through the Milky Way's disk right now, passing through us without us noticing. In fact, at any given moment, trillions of dark matter particles are traversing your body. They pass through you, through the Earth, through everything, without interacting. They are completely transparent to normal matter, except for their gravitational effects. It is a disconcerting idea that we are constantly immersed in an invisible flow of particles that constitute the majority of the universe's mass, but which we cannot directly detect. Scientists have built extremely sensitive detectors, buried deep underground, to try to capture rare interactions between dark matter particles and normal matter. These detectors are shielded by kilometers of rock to block cosmic radiation and other sources of noise. They use tanks of ultra-pure liquid xenon, or special crystals that should glow faintly if a dark matter particle collides with an atomic nucleus. So far, these experiments have not unequivocally detected dark matter. They have set increasingly stringent limits on what properties dark matter can have, ruling out many theories, but without yet providing a definitive detection. It is like searching for a ghost that you know is there because of the effects it causes, but which refuses to appear when you try to observe it directly. And then, there is the cosmic web of dark matter that connects all the galaxies in the universe. The dark matter filaments we saw in the previous chapter form gravitational highways, along which galaxies move and through which gas flows. These filaments can be hundreds of millions of light-years long, but only a few million light-years wide. Astronomers have managed to map this invisible network using ingenious techniques. One involves observing how the light from distant quasars is affected by gas along the line of sight. The gas tends to accumulate along the dark matter filaments, leaving spectral signatures that reveal the three-dimensional structure of the cosmic web. Another technique uses weak gravitational lensing, measuring how the shapes of millions of distant galaxies are subtly distorted by the gravity of the dark matter in the foreground. By analyzing these distortion patterns, astronomers can reconstruct detailed maps of the dark matter distribution across billions of light-years. And what these maps reveal is astounding. The cosmic web of dark matter is surprisingly similar in structure to other complex network systems, such as the neural connections in the brain or the structures of the Internet. There are densely connected nodes, long filaments that connect the nodes, and vast voids with few connections. The universe has organized its invisible matter into patterns that repeat on multiple scales. But perhaps the most unsettling aspect of dark matter is how little we truly understand about it. After decades of study, we still do not know what it is made of. We do not know why it exists in the exact amount that it does, approximately 5 times more abundant than normal matter. We do not know if dark matter particles interact with each other in ways we have yet to detect. There are even alternative theories that propose that dark matter does not exist at all, and that, instead, our theories of gravity are wrong at galactic scales. These modified gravity theories, such as MOND, modified Newtonian dynamics, can explain some observations, but fail to explain others, especially the bullet cluster data. Most physicists are convinced that dark matter is real, but the exact nature of this mysterious substance remains one of the greatest enigmas of modern science. It is humbling to realize that most of the universe is made of something we do not understand, something we cannot see, something we can barely study, except through its gravitational effects. Dark matter is the invisible skeleton of the cosmos, the hidden structure that holds everything visible together. Without it, the universe would be a radically different place, probably one where galaxies never formed, where stars never clustered into the complex structures we observe, and where life, if it could arise at all, would face a much emptier and more hostile cosmos. We live in a universe dominated by the invisible, And the more we learn about dark matter, the more we realize how much we still do not know about the fundamental nature of reality. There is a fundamental limit to what we can see in the universe. It is not a limit imposed by technology or by the sensitivity of our telescopes. It is a limit set by physics itself, by the finite speed of light, and by the finite age of the universe. Astronomers call it the cosmological horizon, and beyond it are galaxies, perhaps an infinite number of them, that we can never observe. Light travels at 300,000 kilometers per second, the fastest possible velocity in the universe. But even at that dizzying speed, light needs time to travel cosmic distances. Sunlight takes 8 minutes to reach us. The light from the nearest star, Proxima Centauri, takes 4 years. The light from the Andromeda Galaxy takes 2.5 million years. And the light from the most distant galaxies we can see has been traveling for more than 13 billion years. But the universe is only 13.8 billion years old. This means that there is a maximum distance from which light has had time to reach us since the Big Bang. That distance defines the cosmological horizon, the boundary between the observable and the unobservable. Beyond that boundary, there are regions of the universe whose light simply has not had enough time to reach us yet. And here is where things get strange. You might think that the cosmological horizon would be 13.8 billion light-years away, the age of the universe multiplied by the speed of light. But you would be wrong. The cosmological horizon is currently at approximately 46 billion light-years away in all directions. How is it possible to see objects that are more than 13.8 billion light-years away if the universe is only 13.8 billion years old? The answer lies in the expansion of space. When the light from a distant galaxy began its journey toward us 13 billion years ago, that galaxy was much closer. But while the light traveled, the space between us and the galaxy expanded, effectively increasing the distance that the light had to cover. Now, that galaxy, whose light has been traveling for 13 billion years, is currently more than 30 billion light-years away due to the expansion. It is like running on a conveyor belt that is moving away from your destination. Although you move forward, the total distance to your goal increases because the space itself is stretching. And there is something even more unsettling. The expansion of the universe is accelerating. In 1998, 2 teams of astronomers independently discovered that distant galaxies are moving away from us faster than theoretical predictions suggested. This accelerated expansion is driven by something scientists call dark energy, a mysterious force that constitutes approximately 68% of the universe's energy content. Dark energy acts like a kind of anti-gravity, pushing space to expand faster and faster. And this has profound consequences for the cosmological horizon. Due to the accelerated expansion, there is a cosmological event horizon, a boundary beyond which galaxies are moving away from us faster than the speed of light. They are not violating the laws of relativity. They are not moving through space faster than light. It is the space itself between us and them that is expanding faster than the speed of light. And this means that the light from those galaxies will never reach us, no matter how long we wait. Every year that passes, approximately 20,000 galaxies cross this cosmological event horizon and disappear from our observable universe forever. It is not that they become fainter until they are undetectable. They literally disappear, their light being stretched by the expansion of space to infinitely long wavelengths until they effectively cease to exist from our point of view. And this is not just a problem for future observers. It is happening right now, at this very moment. As you listen to these words, thousands of galaxies are crossing the cosmological event horizon. Galaxies that we can never study, civilizations that we can never contact if they exist, worlds that we will never know are there, are being torn from our observable universe by the relentless expansion of space. For civilizations that arise in the distant future, 100 billion years from now or more, the night sky will look radically different from ours. They will see only their own galaxy, and perhaps a few companion galaxies in their gravitationally bound local group. Everything else will have disappeared beyond the horizon. There will be no distant quasars, No supernovae in remote galaxies. No evidence that the universe was ever different. These future civilizations would face an almost impossible epistemological challenge. How could they discover the true nature of the universe without evidence of distant galaxies? How could they measure the expansion of the universe without anything moving away? How could they infer the existence of the Big Bang without the cosmic microwave background, which by then would have been stretched to wavelengths so long that it would be undetectable? We, living at this particular moment in cosmic history, are incredibly lucky. We can see billions of galaxies. We can track the expansion of the universe. We can detect the fossil radiation of the Big Bang. We can study quasars in the early universe. All this evidence will eventually be lost to future generations, erased by the accelerated expansion of space. But the cosmological horizon is not the only limit to what we can observe. There is also the problem of the surface of last scattering, the barrier that prevents us from seeing beyond the first 380,000 years after the Big Bang. Before that time, the universe was so hot and dense that it was completely opaque to light. Photons could not travel freely, being constantly scattered by free electrons in the primordial plasma. Only when the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms, could photons finally travel freely through space. This transition, known as recombination, created the cosmic microwave background radiation that we detect today. It is like a wall of light that surrounds the entire observable universe, a snapshot of the cosmos when it was only 380,000 years old. Beyond that wall, the early universe remains hidden from our view. We can never use light to see what happened before recombination. It is a fundamental limit imposed by the physics of the early universe. However, scientists have proposed ways to partially evade this limit using other messengers, gravitational waves or neutrinos that may have traveled freely even in the opaque universe. And then there is the question of what lies beyond the cosmological horizon. Does the universe continue indefinitely? Is it infinite? Or does it have some form of edge or boundary? These questions touch the very foundations of cosmology, and surprisingly, they are difficult to answer definitively. Current observational data suggest that the universe is flat, or very close to flat, in its general geometry. A flat universe can be infinite in extent, stretching forever in all directions. If this is true, then beyond our cosmological horizon, there is a literally infinite number of galaxies, an infinite number of stars, and potentially an infinite number of planets with life. But even if the universe is infinite, we can only interact causally with the portion within our cosmological horizon. Everything beyond that limit is, for all practical purposes, in a separate universe. We cannot send signals there. We cannot receive information from there. We cannot be affected by events that occur there. It is as if those regions did not exist at all from our perspective, and the situation worsens over time. Due to the accelerated expansion, our observable universe will eventually shrink instead of expand. The galaxies that we can currently see will disappear one by one beyond the cosmological event horizon. In the distant future, 100 billion years from now or more, the inhabitants of what remains of our local group of galaxies will see an almost completely empty universe. But there is an even more disturbing idea. Perhaps we are already living in a universe that is emptier than it should be. Perhaps billions of galaxies that existed in the past have already crossed the horizon and disappeared from our sight. We would have no way of knowing how many galaxies have been lost, how much cosmic structure has been swept beyond the reach of any possible observation. Astronomers have calculated that the current rate of galaxy disappearance beyond the horizon is approximately 20,000 per year. That means that every day, approximately 55 galaxies cross the point of no return and disappear from the observable universe. Every hour, 2 or 3 galaxies are lost forever. It is a cosmic countdown toward an emptier and more isolated future, and there is nothing we can do about it. We cannot stop the expansion of space. We cannot reverse the effects of dark energy. We are trapped on a cosmic conveyor belt that is inexorably leading us toward a future of increasing isolation, where eventually all galaxies, except those in our local group, will have disappeared beyond the horizon. But perhaps the most philosophically unsettling thing is this. If civilizations exist in galaxies that are beyond our cosmological horizon, we will never know about them, and they will never know about us. We could be sharing the same physical universe, existing simultaneously in the same space-time, but separated forever by the expansion of space between us. It is like living on different islands of an infinite ocean, with no way to communicate, no way to know that the other exists. The universe could be full of life, teeming with civilizations, rich in biological and cultural diversity, but fragmented by the expansion of space into causally disconnected regions that can never interact. The cosmological horizon reminds us that there are fundamental limits to what we can know about the universe. No matter how advanced our technology becomes, no matter how much our science progresses, there will always be regions of the cosmos that will remain forever out of our reach. The observable universe is not the complete universe, and the difference between the two could be infinite. We live in a bubble of observability, surrounded by a horizon beyond which everything is speculation and theory. And that bubble, far from expanding to reveal more of the cosmos, is gradually shrinking, hiding more and more of the universe from our sight. The future of cosmic knowledge is not one of increasing illumination, but of increasing darkness, as the very evidence of the true nature of the universe is swept beyond the horizon of the observable. And yet, in this moment, now, we have access to more information about the cosmos than future generations ever will. We are privileged witnesses to a universe rich in structure, full of galaxies, where the evidence of the Big Bang is still visible, and where we can trace cosmic history across billions of years. It is a temporary gift of cosmic circumstances, one that will not last forever. Among the billions of galaxies that populate the universe, some defy everything we thought we knew about how these structures form and evolve. Galaxies so faint that they are almost invisible, so diffuse that they look like ghosts in the vacuum of space. Galaxies without dark matter, when all others desperately need it. Galaxies with shapes so perfect that they seem to have been artificially designed. Astronomers call them anomalies, and every discovery of a new anomaly rewrites the rules of the cosmos. The ultra-diffuse galaxies were discovered by accident. In 2015, astronomers using the Dragonfly telescope, specifically designed to detect extremely faint objects, discovered a completely new class of galaxies. These structures are approximately the size of the Milky Way, stretching for tens of thousands of light-years, but contain only approximately 1% of the stars. They are so diffuse that you can literally see through them, observing background galaxies behind their faint glow. The first question that arises is, how can a galaxy be so large but contain so few stars? According to standard models of galactic formation, a structure of that size should contain tens or hundreds of billions of stars. But these ultra-diffuse galaxies have only a few 100 million stars distributed so widely that their surface brightness is less than that of the Earth's night sky. One hypothesis is that these galaxies are dominated almost entirely by dark matter. Perhaps they contain massive dark matter halos that provide the gravitational scaffolding, but for some reason failed to convert much of their gas into stars. Perhaps feedback processes, stellar winds, or black hole activity expelled most of the gas before it could form stars, leaving only the dark matter structure with a minimal stellar population. But then, in 2018, astronomers discovered NGC 1052d F2, an ultra-diffuse galaxy in the Coma cluster that apparently contains no dark matter at all. This was completely unexpected. All known galaxies up to that point were dominated by dark matter, typically containing between 5 and 10 times more dark matter than normal matter. A galaxy without dark matter contradicted decades of established theory. Astronomers measured the velocities of globular clusters orbiting this galaxy and found that they were moving slowly, too slowly, for a massive dark matter halo to be present. The total mass of the galaxy appeared to be approximately equal to the mass of its visible stars, as if someone had stripped the dark matter halo from the galaxy, leaving only the stars behind. But how is it possible for a galaxy to exist without dark matter? Several theories have been proposed. Perhaps the galaxy formed within a larger dark matter halo and was later stripped of its dark matter by tidal forces when passing near more massive galaxies. Or perhaps it formed in very unusual conditions, where for some reason, dark matter did not accumulate in that specific region of space. The discovery was so revolutionary that it generated an intense debate in the astronomical community. Some scientists questioned the measurements, suggesting that the distance to the galaxy might have been calculated incorrectly. If the galaxy were closer than estimated, the velocities of the globular clusters would be consistent with the presence of dark matter. The debate continues, with additional observations attempting to resolve the controversy. And then there are the ring galaxies, structures so perfectly symmetrical that they seem to have been drawn with a compass. The Cartwheel Galaxy, which we briefly mentioned in a previous chapter, is the most famous example. It has a bright nucleus surrounded by an almost perfectly circular ring of young blue stars, all stretching for approximately 150,000 light-years. Ring galaxies are believed to form when a smaller galaxy passes head-on through the disk of a larger spiral galaxy. The impact creates a shock wave that propagates outward, like ripples in a pond when you drop a stone. This wave compresses the gas as it expands, triggering star formation in a circular front that moves outward from the point of impact. But the perfection of these rings is unsettling. Galaxies are chaotic objects influenced by multiple gravitational forces, tidal perturbations, and internal turbulence. That a galactic collision can produce such a symmetrical structure seems almost too ordered, as if the laws of physics conspired to create geometric art in space. And there are other, even stranger anomalies. The Hubble Object Galaxy, discovered in 1950, is an almost perfect ring of young stars, surrounding a spheroidal nucleus of old stars, with an almost complete vacuum between the nucleus and the ring. It is so symmetrical that initially some astronomers speculated it might be a gravitational lensing effect, although subsequent observations confirmed that it is a real galaxy with that extraordinary shape. The strangest thing is that in the space between the nucleus and the ring of Hubble's object, you can see another ring galaxy in the background, perfectly aligned so that it also appears as a ring within the vacuum. It is a cosmic coincidence so improbable that it seems designed. Two extremely rare ring galaxies, perfectly aligned from our point of view. Then, there are the ultra-luminous infrared galaxies, or ULIRGs. These galaxies emit most of their energy at infrared wavelengths, shining with luminosities that can exceed 10 trillion suns. They are enveloped in dense clouds of dust that absorb the ultraviolet and visible radiation from young stars, re-emitting it as infrared radiation. They are typically galaxies in the process of merging, where the collision has triggered extreme bursts of star formation. But some ULIRGs are so luminous that star formation alone cannot explain their brightness. Astronomers believe that many contain hidden quasars, supermassive black holes, voraciously feeding behind impenetrable veils of dust. These galaxies represent a critical phase of galactic evolution, a period of violent transition when collisions trigger both extreme star formation and central black hole feeding. And then there is the problem of submillimeter galaxies, detected only by their emissions at submillimeter wavelengths. These galaxies are completely invisible in optical light due to dust, but shine intensely in the far infrared and at submillimeter radio waves. They existed in large numbers when the universe was only a few billion years old, forming stars at astonishing rates of hundreds or thousands of solar masses per year. The problem is that we do not fully understand how these galaxies were able to accumulate so much gas and form stars so quickly. They represent some phase of galactic evolution that our current models have difficulty explaining. Perhaps galaxy formation in the early universe was much more efficient than we thought. Or perhaps these galaxies are fueled by massive flows of cold gas from the intergalactic medium that our simulations do not adequately capture. There are also galaxies with relativistic jets that stretch for incredible distances. The Alcyoneus radio galaxy, discovered in 2022, has jets that extend for approximately 16 million light-years, the largest galactic structure ever observed. To put this into perspective, these jets are approximately 160 times the diameter of the Milky Way. The supermassive black hole at the center of this galaxy has been launching plasma into space for tens or hundreds of millions of years, creating these monumental structures. How can a black hole maintain such well-collimated jets over such vast distances? Magnetic fields must play a crucial role, but the exact details remain mysterious. And these giant structures are not only spectacular, they have profound effects on the intergalactic medium, heating it and enriching it with heavy elements expelled from the central galaxy. Then, there is the Sloan Great Wall, a structure containing thousands of galaxies, stretching for approximately 100 million light-years, and the aforementioned, even larger, Hercules Corona Borealis Great Wall. These structures are so massive that they defy cosmological predictions. According to the cosmological principle, such large structures should not exist, but they clearly do. Some cosmologists argue that these structures are simply rare statistical fluctuations, improbable but not impossible events in such a vast universe. Others suggest that there might be something fundamentally wrong with our cosmological models, some structure formation process that we are not capturing in our simulations. And there are galaxies with anomalous rotation rates. Some spiral galaxies rotate much faster or much slower than predictions, based on their visible mass and dark matter halos would suggest. These anomalies could indicate that our understanding of dark matter distribution is incomplete, or that there are additional dynamic processes at play that we are not considering. There are also galaxies with anomalous stellar populations. Some galaxies contain stars extremely poor in metals, stars that seem to have formed in almost pristine conditions, similar to those of the early universe, but which exist in relatively modern galaxies. How did this uncontaminated gas survive for billions of years, without being enriched by supernovae and stellar winds? Other galaxies show stellar populations that are too old for the galaxy's apparent age, or populations that have chemical compositions that do not match what we would expect given their history of star formation. Each of these anomalies is a clue that our understanding of galactic evolution is incomplete. And then, there are the objects that defy classification altogether. Blue compact objects, small concentrations of young stars that do not fit comfortably into any established category of galaxy or star cluster. Ultra-faint dwarf galaxies that barely contain more stars than a large globular cluster, but stretch for thousands of light-years. Objects that appear to be galaxies in the process of formation, captured in stages so early in their evolution that they defy our expectations of what young galaxies look like. Each anomaly is a reminder that the universe is more complex, more diverse, more surprising than our theories predict. Galaxies do not follow a single path of formation and evolution. There are multiple possible histories, multiple destinies, multiple ways in which matter can organize itself in the cosmos, and every new anomaly we discover expands our understanding of what is possible in the universe. Perhaps the most humbling thing is to realize that these anomalies we discover are probably just the tip of the iceberg. There are undoubtedly thousands or millions of types of strange galaxies that we have yet to discover, waiting in the data from future sky surveys, or existing in regions of the universe that we have not yet observed in sufficient detail. The universe delights in defying our expectations, in producing objects and phenomena that we did not anticipate, in reminding us that our theories, however elegant, are always approximations of a much richer and more complex reality. And every anomaly we find is an invitation to think more deeply, to question our assumptions, to expand the limits of what we consider possible. The ultra-diffuse galaxies, the galaxies without dark matter, the perfect rings, the impossibly large structures, are all messages from the cosmos, telling us that there is still much that we do not understand about how the universe works. The universe is not eternal. Not even galaxies, those majestic islands of hundreds of billions of stars, will last forever. They have a destiny written in the equations of physics and engraved in the trajectories of cosmic expansion. And that destiny is absolute darkness, absolute cold, absolute isolation. Welcome to the far future of the cosmos, a place where time itself loses its meaning. At this moment, the universe is 13.8 billion years old. It is young in cosmic terms, still vibrant with star formation, still rich in gas for future fuel, still connected by gravity into complex structures. But this golden age will not last. We have already seen how accelerated expansion is separating large-scale structures. Now, we will see what happens when we follow that trend to its final logical conclusion. In approximately 4.5 billion years, the Milky Way will collide with Andromeda. This merger will be one of the most transformative events in the history of our galactic neighborhood. Over the course of several billion years, the two galaxies will interpenetrate, separate, and collide multiple times before finally merging into a single giant elliptical galaxy that astronomers have dubbed Milkomeda. By then, in approximately 6 billion years, the Sun will have evolved into a red giant, swelling to potentially consume the orbits of Mercury, Venus, and perhaps the Earth. Afterward, the Sun will expel its outer layers as a planetary nebula, leaving behind a white dwarf, a stellar corpse the size of the Earth. But with approximately half the mass of the Sunday, the white dwarf will gradually cool over trillions of years, fading from brilliant white to yellow, to red, and finally to black. In approximately 100 billion years, all the galaxies that we can currently see in the night sky, except for those in our local group, will have disappeared beyond the cosmological horizon. Milkomeda, along with the Triangulum Galaxy and a few satellite dwarf galaxies, will be alone in a seemingly empty universe. An observer in that distant future would see an almost completely black night sky, with only the stars of their own galaxy visible. There would be no evidence that billions of other galaxies ever existed. In 1 trillion years, star formation in the universe will have declined dramatically. Most of the available hydrogen gas will have been converted into stars or expelled from galaxies by stellar winds and supernova explosions. The last generations of stars will be forming mainly small, long-lived stars known as red dwarfs. These small stars can live for trillions of years, much longer than the current age of the universe. In 10 trillion years, star formation will have essentially ceased entirely. All the massive stars will have died long ago, exploding as supernovae or collapsing into black holes. Intermediate mass stars like the Sun will have evolved through their red giant phases and become white dwarfs. Only the lowest mass red dwarfs will still be shining, but even they will eventually exhaust their fuel. In 100 trillion years, the last red dwarfs will go out. The universe will enter the degenerate era, an epoch dominated by dead stellar objects, white dwarfs, neutron stars, and black holes. Galaxies will still exist as gravitationally bound structures, but they will no longer shine. They will be dark cemeteries floating in an increasingly cold vacuum. But even these dark structures are not stable. The dead stars in galaxies will occasionally collide with each other, an extremely rare process, but inevitable given enough time. When two white dwarfs collide, they can merge, and if their combined mass exceeds approximately 1.4 solar masses, the Chandrasekhar limit, they can explode in a thermonuclear supernova. These occasional flashes of light will be the only brilliant events in an otherwise completely dark universe. Also, the gravitational interactions between the dead stars will cause some to be ejected from their galaxies at high velocities, while others will lose energy and fall toward the supermassive black hole in the galactic center. Over time, during the course of approximately 10 to the 19 or 10 to the 20 years, most of the dead stars will have been ejected into intergalactic space or devoured by the central black hole. By then, galaxies as structures will have ceased to exist. In their place will be isolated supermassive black holes, surrounded by tenuous halos of dead stars, floating in a universe that has become incomprehensibly empty and cold. The temperature of the universe, which is currently approximately 3 degrees Kelvin, due to the cosmic microwave background radiation, will have dropped to fractions of a degree above absolute zero. In 10 to the 34 years, even white dwarfs will begin to disintegrate. Although they are composed of extremely dense, degenerate matter, they are not absolutely stable on such vast timescales. The protons in their nuclei will eventually decay, assuming protons are not absolutely stable, something that current particle physics suggests, but has not definitively confirmed. Proton decay would gradually convert white dwarfs into diffuse radiation. In 10 to the 40 years, even neutron stars and stellar black holes will have evaporated. Stephen Hawking demonstrated in 1974 that black holes are not completely black. They emit an extremely faint radiation, known as Hawking radiation, due to quantum effects at the event horizon. This radiation causes black holes to lose mass extremely slowly. For a black hole the size of those formed by stellar collapse, the evaporation time is approximately 10 to the 67 years. For the supermassive black holes in the centers of galaxies with masses of billions of suns, the evaporation time is approximately 10 to the 100 years. These numbers are so vast that they defy any comparison. 10 to the 100 years is a 1 followed by 100 zeros. The current age of the universe of 13.8 billion years is barely a blink compared to these timescales, but eventually even the most massive black holes will evaporate, and when they do, the universe will enter the final, dark era. There will be no structured matter of any kind, no stars, planets, galaxies, or black holes. Only an extremely diluted sea of subatomic particles and photons, distributed so sparsely that the average distance between particles will be greater than the current size of the observable universe. The temperature of the universe will be inconceivably close to absolute zero. The density will be effectively zero. Time, although technically still measurable, will have lost all meaning because there will be no physical processes occurring, no change, no events. The universe will have reached a state of maximum entropy, what physicists call heat death. But there are some even stranger speculations about the ultimate future of the universe. Some physicists propose that even in this final era, extremely rare quantum fluctuations may occur. On timescales of 10 to the power of 10 to the 50 years or more, there is a tiny probability that spontaneous quantum fluctuations could temporarily create complex structures, potentially including complete conscious brains with false memories. These Boltzmann brains would be more likely than the spontaneous emergence of complete universes, raising profound philosophical questions about the nature of observation and reality. Another possibility is that the quantum vacuum of spacetime is not absolutely stable. If a lower energy state exists, the universe could eventually undergo a catastrophic phase transition known as false vacuum decay. A bubble of true vacuum would form somewhere in space and expand at the speed of light, rewriting the laws of physics within it. This would instantaneously destroy all the structure of the universe as we know it. Or perhaps dark energy is not constant. If dark energy increases over time, it could lead to a scenario known as the Big Rip. In this future, the accelerated expansion would become so intense that it would eventually tear apart all gravitationally bound structures. First, galaxy clusters would be torn apart, then individual galaxies, then stellar systems. Finally, even atoms would be ripped apart by the expansion of space. The universe would end in a singularity of infinite expansion. Alternatively, if dark energy decreases or becomes repulsive, the universe could eventually stop expanding and begin to contract, leading to a big crunch. All matter and energy in the universe would collapse back into a dense, hot singularity, possibly rebounding into a new Big Bang, initiating an eternal cycle of expansion and contraction. But according to our best current understanding, the most probable scenario is the gradual heat death we described. The universe will continue to expand forever, becoming increasingly colder, darker, and emptier, until finally, nothing is left except extremely dispersed radiation in an almost infinitely large space. And in this distant future, there will be no one to witness the end. Life, if it managed to evolve in multiple places in the universe, will have disappeared eons ago. The civilizations that may have arisen, potentially including civilizations much more advanced than ours, will have faced the same inevitable destiny. The heat death of the universe makes information processing impossible, and therefore, life as we understand it, impossible. Some physicists have speculated about ways advanced civilizations might survive for extremely long periods of time by building computers that operate increasingly slowly as the universe cools, taking advantage of the last drops of available energy. But even these strategies would eventually fail when no usable energy remains in any form. The universe that began in a brilliant flash of creation will end in absolute darkness and absolute silence. All the galaxies, all the stars, all the planets, all the life, all the consciousness, all the beauty and complexity that arose during billions of years of cosmic evolution will eventually fade into nothingness. It is a melancholic destiny, perhaps even terrifying in its inevitability. But there is also something profound in recognizing that our time in the universe is precious, precisely because it is temporary. We live at a special moment in cosmic history, when the universe is rich in structure, full of light, capable of sustaining complexity and consciousness. And in this fleeting moment of cosmic illumination, we have managed to develop the capacity to understand our place in the vast tapestry of space and time. We can look back to the first moments after the Big Bang. We can look forward to the final destiny of the universe. We are stardust that has become conscious, capable of contemplating both our origin and our end. The final destiny of all galaxies is darkness. But before that darkness arrives, there are billions of years of wonder, beauty, and possibility. And we have the privilege of existing in the midst of it all. We have traveled across billions of light years, from the most remote confines of the observable universe to the distant future where all the stars will go out. We have explored galaxies that devour each other, black holes that govern the destiny of entire worlds, and structures so vast that they defy comprehension. But now, in this final moment of our journey, we must reflect on what all this means for us here, now, on this small planet, orbiting a common star in a galaxy that is barely one among billions. There is a fundamental truth that runs through everything we have discussed. We live at an extraordinarily privileged moment in cosmic history. Not just privilege because we exist, not just privilege because we are conscious, but privilege because we can observe. We can see billions of galaxies scattered across the sky. We can detect the fossil radiation of the Big Bang. We can trace the history of the universe from its first moments to the present. Civilizations that arise in the distant future will not have this privilege. They will see an almost empty sky, devoid of distant galaxies, with no clear evidence that the universe had a beginning or that it was ever different. We, on the other hand, live in the golden window of cosmic observability, when the evidence of the universe's past is still visible and accessible. Every photon of light from a distant galaxy that we capture with our telescopes has traveled for billions of years through the vacuum of space to reach us. That photon began its journey when the universe was younger, hotter, and denser. Perhaps it was emitted by a star that exploded as a supernova long ago. Perhaps it traversed clouds of interstellar gas. It was deflected by gravitational fields, stretched by the expansion of space, and at the end of its epic journey, it landed in our telescope's detector, delivering a message from a distant time and place. Each of these light particles is a messenger from the cosmos, and we, through physics, mathematics, and technology, have learned to read these messages. We can analyze the light of a distant galaxy and determine its chemical composition, its temperature, its velocity, its age, and its history. We can reconstruct entire narratives of cosmic evolution from subtle patterns in the light we receive. It is extraordinary when you think about it. We are creatures evolved on a planet where survival depended on finding food, avoiding predators, and reproducing. And yet, We have developed the capacity to understand phenomena that occur on scales of distance and time that are completely alien to our everyday experience. We can conceive of billions of years. We can imagine billions of light years. We can reason about the conditions in the core of a black hole or in the first seconds after the Big Bang. This capacity to transcend our biological limitations through reason and observation is perhaps the most remarkable achievement of the human species. We are not the strongest animals, nor the fastest, nor the most resilient, but we are the ones who look up at the stars and ask what they are, how they work, where we come from, and where we are going. And although the answers we have found are often humbling, revealing our insignificance in the vast cosmic scheme, they are also deeply inspiring. We are part of a universe that generates complexity, that allows the emergence of structure from chaos, that makes possible the existence of conscious observers who can reflect on their own origin. Every atom in your body was forged in the interior of a star that exploded billions of years ago. The oxygen in your lungs, the carbon in your DNA, the calcium in your bones, the iron in your blood, all were created by nuclear fusion in stellar furnaces. You are literally stardust organized in such a way that it has become conscious. You are the universe experiencing itself, and the fact that we exist at all is extraordinary. The conditions necessary for life, as we know it, are incredibly specific. If the fundamental constants of physics were slightly different, if the expansion of the universe were a little faster or slower, if dark matter did not exist, or existed in different quantities, the universe might be a place where galaxies never formed, where stars never ignited, where life never had a chance to arise. We live in a universe finely tuned for complexity, and within that universe, we exist on a planet that orbits in the habitable zone of its star, with a magnetic field that protects us from cosmic radiation, with an atmosphere that sustains life, with liquid water on its surface. The probabilities of all these conditions aligning are infinitesimally small, and yet, here we are. But our existence is also incredibly fragile. The universe is a vast and mostly hostile place to life. The space between stars is an almost perfect vacuum, with temperatures barely above absolute zero. Galaxies collide in events of unimaginable violence. Black holes devour everything that gets too close. Supernovae sterilize entire planets with radiation, and the accelerated expansion of the universe will eventually separate all structures, ultimately leading to the heat death of the cosmos. We are like candles lit in the middle of a hurricane, struggling to keep our flames alive against forces that are vastly and incomprehensibly greater than us. And yet, here we are, not only surviving, but thriving, not only existing, but questioning, exploring, and discovering. And there is something profoundly important in the act of looking up and marveling at a universe that will eventually end in darkness and cold. The fact that conscious creatures have arisen and dedicated time and energy to understanding the cosmos is in itself an act of defiance. It is as if the universe were looking at itself through our eyes, becoming conscious of its own existence before everything fades into nothingness. Each generation of human beings inherits the accumulated knowledge of previous generations. The ancient Greeks looked at the stars and wondered what they were. Medieval astronomers charted the movements of the planets with primitive instruments. Galileo pointed his telescope at the sky and discovered moons orbiting Jupiter, proving that not everything revolves around the Earth. Edwin Hubble discovered that the universe is expanding, revolutionizing our understanding of the cosmos. Vera Rubin discovered dark matter, and today we continue that tradition, building more powerful telescopes, developing more sophisticated theories, and unraveling deeper mysteries. This process of discovery will not end with us. Future generations will continue to explore, asking questions we have not yet thought of, discovering phenomena that we cannot even imagine. The universe still holds innumerable secrets, and the process of revealing them is an adventure that has barely begun. But we must also recognize that our time to observe the universe in all its glory is limited, not only in the individual sense of our finite lives, but in the cosmic sense. As we have seen, the accelerated expansion of the universe is gradually hiding more and more of the cosmos from our sight. Every year that passes, thousands of galaxies disappear beyond the cosmological horizon. The window of observability is slowly closing. This gives urgency to our efforts to understand the universe. We do not have forever to make these observations. Future generations will have access to less evidence. They will see a more impoverished cosmos. We are like archaeologists, working at a site that is being gradually eroded by the wind and time, knowing that if we do not document what we find now, it will be lost forever. And there is another reason why this knowledge is important. It gives us perspective on our place in the universe. The everyday concerns that dominate our lives, however important they may be to us personally, are infinitesimal in the grand cosmic scheme. Our entire civilization, with all its history, its wars, its achievements, its tragedies, has existed for barely a few thousand years in a universe of billions of years. But this does not make our existence meaningless. On the contrary, it makes it more precious. We are rare, perhaps extraordinarily rare, in a vast universe. Conscious life might be one of the rarest phenomena in the cosmos, and the fact that we exist at all, that we can reflect on these questions, that we can marvel at the immensity of the universe, is a temporary gift of cosmic circumstances. So while you are here, in this fleeting moment of cosmic illumination, take a moment to appreciate the amazing truth of your existence. You are made of atoms that were forged in ancient stars. You live on a planet that orbits one of 100 billion stars, in a galaxy that is one of 2 trillion galaxies in the observable universe. And despite these astronomical odds, you are here conscious, capable of contemplating all of this. The universe is vast beyond all comprehension. It contains mysteries that we may never completely solve. It is destined to eventually end in darkness and cold. But before that end arrives, there is this bright moment of complexity, structure, life, and consciousness. And you are part of that. The galaxies we have explored tonight, with their monstrous black holes, their violent collisions, their final destinies in the darkness, are all part of the same cosmic story that you and I are a part of. We are connected through time and space, by the laws of physics, by the common origin of all atoms, by the fact that we are all temporary inhabitants of this extraordinary universe. And the more we explore, the more we realize that what we know is barely a flash compared to the vast expanse of the unknown. The cosmos still holds innumerable secrets waiting to be discovered. Mysteries that will keep generations of scientists busy to come. Wonders that we have barely begun to imagine. What mystery of these billions of galaxies astonished you the most? Was it the existence of invisible dark matter that holds all the visible structure together? The supermassive black holes that govern the destiny of entire worlds? The final destiny of the universe in absolute darkness? Or perhaps the realization that we live at a unique moment where we can still observe the immensity of the cosmos? Leave a comment below to join this conversation about the deepest mysteries of existence. Do not forget to like, subscribe to Night Science, and turn on notifications to continue exploring the amazing secrets of the universe with us. Because every night we look up at the stars, we are witnessing a spectacle that future generations will never be able to see. And that privilege, that temporary window of observation, is one of the most extraordinary gifts the cosmos has given us. Good night, and may your dreams take you through the billions of galaxies that populate this amazing universe.